Welcome, everyone. This is part 2 in our series on contextual word representations. We're going to be talking about the transformer architecture, which is the central piece for all the models we'll be exploring in this unit. Let's dive into the model structure. We'll work through this using a simple example. At the bottom here, I've got the input sequence, the rock rules, and I've indicated in red that we're going to be keeping track of the positions of each one of those tokens in the sequence. So the first step is a familiar one. We're going to look up both the words and the positions in separate embedding spaces. Those are fixed embedding spaces that we'll learn as part of learning all the parameters in this model. I've given the word embeddings in light gray and the positional embeddings in dark gray. To form what we think of as the actual embedding for this model, we do an element-wise addition of the word embedding with the positional embedding. And that gives us the representations that are in green here. You can see that on the right side of the slide, I'm going to be keeping track of all of the calculations with regard to this C column here, and they're completely parallel for columns A and B. So to form C input, we do element-wise addition of X34, the embedding for the word rules, and P3, which is the embedding for position 3 in this model. The next layer is really the hallmark of this architecture and what gives the paper its title, Attention is All You Need. We're going to form a bunch of dense dot product connections between all of these representations. So you can think of those as forming these connections that look like this, a dense thicket of them. On the right here, I've given the core calculation, and it should be familiar from part 1 in this unit. It's exactly the calculation I presented there with just 2 small changes. But fundamentally, if our target vector is C input here, we're attending to inputs A and B. We do that by forming the dot products here. And the one twist from before is that instead of just taking those dot products, we'll normalize them by the square root of the dimensionality of the model dk. dk is an important value here because of the way we combine representations in the transformer. All of the outputs at all the layers we look at have to have the same dimensionality as given by dk. And so what we're doing here is essentially scaling these dot products to kind of keep them within a sensible range. That gives us a score vector alpha tilde. We softmax normalize that. And then the other twist is that instead of using mean here as we did before, we use summation. But the actual vector is the one we calculated before. We're going to take weighted versions of A input and B input according to this vector of weights that we created here. That gives us the representation C attention as given in orange here. And we do that, of course, for all the other positions in the model. The next step is kind of interesting. We're creating what's called a residual connection. So to get CA layer here in yellow, we add up C input and this attention representation that we just created and apply dropout as a regularization step there. And that gives us CA layer. The interesting thing there, of course, is this residual connection. Instead of simply feeding forward C attention, we feed forward actually a version of it that's combined with our initial positionally encoded embedding. Then we follow that with a step of layer normalization, which should help with optimization. It's going to kind of scale the weights in these representations. The next step is more meaningful. This is a series of 2 dense layers. So we'll take CA norm here and feed it through this dense layer with a nonlinearity, followed by another linear layer to give us CFF as given in dark blue here. And that's followed by another one of these interesting residual connections. So we'll apply dropout to CFF and then add that in with CA norm as given down here at the bottom. And that gives us this second yellow representation. And we follow that by one more step of layer normalization, and that gives us the output for this block of transformer representations. And you can imagine, of course, as you'll see, that we can stack up these transformer blocks. And the way that we do that is essentially by taking these dark green representations at the top here and using them as inputs. And all the calculations are the same. So you might imagine that we could continue here by just doing a dense series of attention connections across these, and then continuing on with the calculations I just presented. And in that way, we could stack up transformer blocks. And I'll return to that later on. There are a few other things that are worth pointing out that are kind of noteworthy about this model. It looks like a complicated series of calculations, but I would say that fundamentally what's happening here is we're doing positional encoding to get embeddings so that they are position-sensitive representations of words. We follow that with an attention layer, which creates that dense thicket of connections between all of the words as positionally encoded. Then we have these optimization things woven in, but fundamentally we're following that attention step with 2 series of feed-forward layer steps here, followed by the same process of dropout and layer normalization. So if you kind of elided the yellow and the purple, you would see that what we're really doing is attention followed by feed forward. And then as we stack these things, it would be attention, feed forward, as we climbed up. And interwoven into there are some things that I would say help with optimization. Another noteworthy thing about this model is that the only sense in which we are keeping track of the linear order of the sequence is in those positional embeddings. If not for them, the column order would be completely irrelevant because, of course, we've created all of these symmetric connections at the attention layer, and there are no other connections across these columns. So the only sense in which column order, that is word order, matters here is via those positional embeddings. Here's a more detailed look at the attention calculations themselves. I just want to bring out how this actually works at a mechanical level. So this is the calculation as I presented it on the previous slide and in part 1 of this unit. In the paper, and now commonly, it's presented in this matrix format. And if you're like me, it's not obvious right away that these are equivalent calculations. So what I've done for these next 2 slides is just show you via worked out examples how those calculations work and how they arrive at exactly the same values. I'm not going to spend too much time on this here. This is really just here for you if you would like to work through the calculations in detail, which I strongly encourage because this is really the fundamental step in this model. And here's all the details that you would need to get hands-on with these ideas. Now, so far I've presented attention in a kind of simplified way. A hallmark of attention as in the transformer is that it is typically multi-headed attention. So let me unpack that idea a little bit concretely. We'll start with our input sequence from before, and we'll be looking at these green representations here. And the idea behind the multi-headed attention mechanism is that we're going to inject a bunch of learned parameters into this process to encourage diversity as part of the learning process and learn really diverse and interesting representations. So here's how that works. We're going to form 3 representations here using that same dot product mechanism as before. And fundamentally, it's the same calculation, except now we're going to have a bunch of learned weight parameters as given in orange here. And those will help us with 2 things. First, injecting diversity into this process, and also smooshing the dimensionality of the representations down to 1/3 of the size that we're targeting as dk for our model dimensionality. And you'll see why that happens in a second. But fundamentally, what we're doing is exactly the calculation we did before, but now with these learned parameters injected into it. So if you squint, you can see that this is really the dot product of C input with A input as before, but now it's transformed by these learned parameters that are given in orange. And that repeats for these other calculations. So we're going to do that for position A, and we do it also for position B. And it's the same calculation, but now with new parameters for the second position. And then for the third head, exactly the same calculation, but new learned parameters up at the top here. So this is 3-headed attention. And the way we actually form the representations that proceed with the rest of the calculation in the transformer architecture as presented before is by concatenating the 3 representations we created for each one of these units. So the A column is the first representation in each one of these heads. The B column is the second representation in each head. And similarly for the C column as the third representation in each one of these heads. And that's why each one of these needs to have 1/3 the dimensionality of our full model so that we can concatenate them and then feed those into the subsequent calculations. And the idea here, of course, is that injecting all of these learned parameters into all of these different heads, we're providing the model a chance to learn lots of diverse ways of relating the words in the sequence. The final point is one I've already mentioned before, which is that typically we don't have just one transformer block, but rather a whole stack of them. We can repeat them n times. For models you're working with, you might have 12 or 24 or even more blocks in the transformer architecture. And the way we do that, as I said, is simply by taking the dark green representations at the output layer here and using them as inputs to a subsequent block. So they get attended to, and we proceed with the subsequent regularization and feed forward steps just as before. And when you work with these models in Hugging Face, if you ask for all of the hidden states, what you're getting is a grid of representations corresponding to these output blocks in green here. And of course, just as a reminder, I'm not indicating it here, but there's actually multi-headed attention at each one of these blocks through each one of the layers. So there are a lot of learned parameters in this model, especially if you have 12 or 24 attention heads. At this point, I'm hoping that you can now fruitfully return to the original Vaswani et al. Paper and look at their model diagram and get more out of it. For me, it's kind of hyper compressed, but now that we've done a deep dive into all the pieces, I think this serves as a kind of useful shorthand for how all the pieces fit together. So let's just do that quickly. As before, we have positional encodings and input word embeddings, and those get added up to give us the intuitive notion of an embedding in this model. That's followed by the attention layer, as we discussed, and it has a residual connection here into that layer normalization part. That's fed into the feed forward blocks, and that's followed by that same process of kind of dropout and layer normalization. And this is essentially saying each one of these is repeated for every step in the encoder process, every one of the columns that we looked at. Right, and because in the paper they're working with an encoder-decoder model, each decoder state self-attends with all of the fellow decoder states and with all of the encoder states. So, right, imagine this double sequence. We have a dense series of attention connections across both parts of the representation. On the right side, when we're doing decoding, again, we repeat this block for every decoder state. And if every state there has an output, as for machine translation or some kind of generation process, then we'll have something like this output stack at every one of those output states. If, by contrast, we're doing something like NLI or sentiment, it's a classification problem, maybe just one of those states will have one of these outputs on it. And then the attention gets a little bit complicated if you are doing decoding for a model like natural language generation or machine translation. In the decoder, you can't attend into the future as you're doing generation. So there's a masking process that limits self-attention to the preceding words in the sequence that you're creating.